Welcome everyone to TrojAI's webinar series. Today we're going to be talking about agent-led AI red teaming, and we're super excited to be here. I am Julie Peterson. I am the lead product marketing manager here at TrojAI. I have worked in security for the last few years, more years than I'm going to admit out loud to all of you. And I'm joined today with two great experts on AI security. Amer, why don't you introduce yourself?
Yeah, sure. I'm Amer Hassounah. I'm on the software development team, mostly focused on the Detect side of our platform. And AI agent-led teaming, AI agent red teaming is one of the products we just recently released in our Detect stream, and we're really excited actually today to talk to you about it and just show you what we've done and all the capabilities it's going to be able to bring to your organization.
Or?
My name's Or Brown. I lead sales engineering here at TrojAI. I've been at TrojAI for almost 2 years now, but have a long background in security, specifically in threat detection and incident response.
Great. It's going to be a fabulous, I was going to say show today, but fabulous webinar. So we're all excited to have you here. Just a quick run through of the agenda. We're going to talk about the reason we're all here, which is the increase of AI risks, and talk specifically about our agent-led AI red teaming solution. Or is then going to do a great demo, and we'll round it out with a Q&A session. And just as a reminder, at the bottom of your screen, there should be a Q&A box. That is where you can add your questions. And if we can, we'll try to answer them along the way, but generally we usually hold all questions to the end, and we'll answer as many as we can at that point. So again, put your questions in the Q&A box and we will get to them at the end. So now let's get down to it. So security, I don't think this is going to be a shocking statement, but security has always chased technology. We saw that with the cloud. We saw that with the move to web applications. And we're definitely seeing that now with AI, right? Security is lagging. It's always struggling to keep up. I think what's different about AI compared to other advances and shifts in technology is that the speed with which AI systems are evolving is just faster than anything we've seen before. I don't think that's a controversial statement, right? You guys agree with me, right, Amer?
I completely agree with you. It has accelerated software development and other fields to the point where you can roll out new software faster. You can roll out new technologies and stacks faster. And at the same time, the technology itself is advancing at an accelerated rate. It's the concept of using the technology itself to accelerate itself. And we see that concept in practice all over now. And that's only going to increase the speed at which this technology is going to continue advancing. And so, one of the things we've realized is that we have to build systems to keep up with the technology as it's advancing. And this is where, we started the thinking of those agent-led AI red teaming systems of how can we utilize that technology as it's advancing to be able to, safely secure it as well.
Yeah, and I think also you're right. We need new technology to keep up with it, but also we need to have teams quickly build their knowledge around it. And so tools that do that will help them keep up with these evolving threats. I think, one of the other things
that's a very excellent point, I think, Julie, because the landscape we've noticing is the expert humans in these systems. There's a lot of them, but also not enough. There's a lot of adoption of these AI systems, but there isn't enough human expertise to reliably be able to exercise and test those systems.
Yeah, definitely. Like 2 years ago, there was no such thing as an AI security architect. And we're seeing more and more of that now. Companies are building teams for sure. So we're moving in the right direction, but just the speed with which things are changing, the challenge to keep up with. And then I think also, the systems themselves don't fail in neat and tidy ways anymore. There isn't a single input that's going to predictably cause a failure of the same output that you can, log, uh, capture, move on from, right? We're going to remediate this one problem and then we're done with it. That's just not how these systems work. Failures are emerging across interactions and across agents, right? Agents add another layer of complexity. And then sometimes only after a chain of, what might be seemingly harmless events do you actually have a real risk emerge. So again, adding to the complexity there. And then I think we're definitely seeing changes. But in the past or in the early days, security teams were kind of treating, these AI systems as if maybe they were an API with a personality, or they kind of really weren't taking in the stochastic nature of AI systems. And the reality is that these systems are more like a participant in a conversation, and that conversation can go off the rails at any time, right? I sort of think about it as like your friend who 9 times out of 10 has an appropriate response, but that one time he's going to say something that's just so off the wall that, it renders him unpredictable like the whole time. And that's kind of how we have to think about these systems. So
this is a really good point, because these systems by design are predicting probabilities, right? So an LLM, that's what it's doing. It's predicting probabilities and generating the next token. So when you build a system on top of that, at best, like you mentioned, 1 time out of 10, you're going to get a behavior that you're not expecting.
Yeah, definitely. So, we have a gap, and our company is developing tools, but just in general, you need to develop tools and systems to put in place to close that gap and reduce your risk. The problem is that traditional red teaming approaches, which made a lot of sense when systems were simpler, just really aren't applying. In the past, you could send a prompt, get a response, and then evaluate whether that prompt or the response violated a policy. And that works when you have simple interactions, but modern AI systems are so much more sophisticated. And so now they maintain context, they can call tools, they interact with other agents, they build state over time. And so you can't really find vulnerabilities in single interactions. You have to really have some kind of sequence or multi-step to find these vulnerabilities. I think of like earlier testing as being a snapshot, and that snapshot is like super useful. It's not that it doesn't have a use, but it's just like a static picture where we kind of need to see the whole picture to understand where critical risks are lying in systems today.
But also, when you think about it, those systems are not traditionally tested in the same way we think of traditional red teaming, right? Because in a way, traditional red teaming in network security, for example, involved exposing vulnerabilities and security issues. But with AI-backed applications, that's not always the case. Let's think of the use case where you have an AI application that's trying to provide information, whether it's regarding legal, health, or any other sensitive topics. Now, you want those systems to be able to answer those questions, but at the same time, you want them to provide proper disclaimers. This is so when you want to test those systems, you're not testing for traditional vulnerabilities, you're also testing for behavioral type exploitations, where can I get a medical AI agent, for example, to answer questions without providing the proper disclaimers of the information it's providing. So it just increases those attack surfaces and how you can exploit those applications.
Yeah, great point. Great point. So I think we've touched upon a lot of it, but there's a few structural reasons why this problem is getting bigger. And obviously the first one is agent to agent interactions. As soon as you introduce these multiple agents, agents that can call each other, you're not dealing with a single system, you're dealing with multiple systems, you're not adding, you're multiplying. And you're testing a network of decisions. And each of these handoffs can represent a potential point of failure. So agents, again, Amer, I'm sure you've seen a lot of just how that adds to the complexity and the risk.
You're absolutely right. Like exactly as you mentioned, at every step of the way, you're compounding that risk, you're multiplying by that risk, because every non-deterministic behavior across the chain increases that attack surface and increases how the entire chain is going to behave. So, the more of these agent chains that you build to roll out, the more compounding the effect of any of these failures along the chain. And so, the risk is growing at, I dare say, at an exponential rate when you're trying to add all of these complex systems together.
Mm-hmm. Right. And then making this problem even more difficult to solve is that these agents can now call tools. And we see these AI systems, they're able to take actions, they can query data, they can trigger workflows. And so now you're introducing these indirect paths to exploitation. The model doesn't have to fail directly. It just needs to take a wrong step at the wrong time. There was a couple of weeks ago an exploit, I don't want to name the company, but where a database in production was deleted in 9 seconds. And in defense of the security team, the agent in question that did this action was in a sandbox and it shouldn't have had access to production tools. And when it did it, and it explicitly had instructions not to do actions like delete something in production. And when it did it and it was queried afterwards, basically the agent said, my bad. It was essentially its reaction of like, oh yeah, I know I wasn't supposed to do it. I did it. Sorry. And again, these are the kinds of things that we're dealing with, right? So you even when you think you understand how a system behaves, it's gonna respond differently in different situations.
Right. And you bring a very good point about tool use. Tools are extending the LLM's capabilities to reach into your resources. Tools are allowing your agents to access things that they may not have had access before. So being able to exercise these tools, being able to, get a lay of the land of what the agent is doing in a safe environment is definitely something that is needed. It's becoming more and more of a requirement now, more so than ever before. Again, we go back to the non-deterministic behavior that these agents can bring to the table. And if you don't have enough guardrails around, if you don't have enough protections, if you don't thoroughly test their behavior throughout, you're not really guaranteed to know how to expect they're going to behave in production, really.
Yeah. Right. So we're not just dealing with, this rapid volume and expansion of technology in use, but we're also, the complexity is just through the roof. All right. So I think, most of us here understand what red teaming is because you're here. But just to set a baseline at a high level, red teaming is acting like an adversarial, intentionally trying to break your system so that you can understand where the weaknesses are. With AI, you need to expand that definition a bit because you're not testing code anymore. You're not testing sort of inputs and expecting to get the same outputs. You're testing how a system responds under pressure, how it handles ambiguity, and how it evolves across multiple interactions. And that can include different misuse and abuse scenarios and understanding unintended outputs. Amer, you had said earlier, you'd given the example of like maybe a chatbot giving medical information without a proper disclaimer. So
Right. When we think about AI red teaming, exactly as you're describing, it's no longer a code vulnerability. It is now also part of it is a behavioral vulnerability. Is the system behaving in the way we expect it to behave? Is it doing this work that we expect it to do? Is it doing something different? Now, when we want to try and simulate some of this behavior, in a way, we have to think about how attackers are actually attacking these systems. They're not really waiting for us to, they're not waiting for production grade systems. They're putting together scripts that just iterate endlessly at scale to try and expose some of these behavioral vulnerabilities. So what we're trying to capture with our AI red teaming is a way to simulate some of that behavior and provide peace of mind of knowing that if your system is attacked in these patterns, you have a way of knowing how your system will behave.
Yeah, right. And yeah, I think kind of how I like to think about it is we've moved from can I make the system fail to how does it fail? What does that failure look like in a real world scenario? Because that's what ultimately determines risk. All right. So I'm going to pass it over to you, Amer, to do the next few slides. So
Thanks,
you
Julie.
know, yeah, no problem.
So what we want to do here is, talk a tiny bit about the journey to get to AI agent red teaming. When we first set off to start doing assessments for generative AI, the first and this is probably very very well known to everybody attending is you want to simulate single turn attacks. You have one prompt, you send it to the system, and then you evaluate the response you get from that system. Now, this helped us establish baseline checks. We had curated data sets that were testing for specific behaviors. Can an AI application generate harmful content? Can an AI application generate misinformation? Can an AI agent give medical advice without disclaimers? You have curated data sets, single prompts, test specific for those behaviors. As the technology advanced, and it advanced very quickly, models themselves got better at protecting from these answers. The API guardrails around those systems got better at detecting. The applications themselves utilizing those got better. But that doesn't mean you want to stop checking for those things. This is your baseline check. This is where when you're rolling out an AI application or an AI agent, you want to make sure that at least it has this basic baseline behavioral check of it's not producing harmful content. It's not giving misinformation. It is giving the proper disclaimers. So all of that is still just as relevant today as it was, a few years ago when generative AI was starting to roll out. So, while we consider this the beginning of our journey, it is still a fundamental part of everything that we still do, even in the age of agent red teaming. Maybe we can move on now to the next phase. So after we captured the curated data sets, the research advanced. There's a ton of AI red teaming researchers out there trying to find different ways to expose these behaviors. And the next step from that was to utilize different algorithms and techniques to try and distract the AI application or the agent or the LLM into answering those harmful questions or prompts. This is where the context of the conversation makes a big part of this attack pattern. You try, a lot of the algorithms we know, for example, in patterns of building trust in a few turns and then asking your harmful question, building a distraction layer of getting the model distracted by previous parts of your conversation, or even leading a dynamic style conversation. And this is where, when we look at multi-turn, we look at it as two types of multi-turn. We have the scripted multi-turn, and those are scripts that researchers have come up with. They're proven. They are known to produce certain behaviors. For example, bad Likert scale is a known attack pattern where you give the LLM essentially a bad scale and trick it into producing harmful content. It's a script. There's certain turns to it, and that's how you perform the attack. Now, on the other side of multi-turn, we also have what we call dynamic multi-turn, where the conversation is generated on the fly, where essentially we're pitting one AI application against another. One AI application is primed to produce and lead a conversation to trick another AI system into producing harmful content. And this is where the dynamic part of it happens. The attacker system is given instructions on how to produce that conversation, and then it iterates on its own to try and produce that conversation. And this was the next evolution of us trying to produce reliable assessments. Now, once we had the data sets for single turn, we had the algorithms and the manipulation techniques for multi-turn and single turn. We have over 100 plus different manipulation techniques that can be applied to prompts. We have 30 plus data sets that can be used. We have now over 15 to 20 different multi-turn attack algorithms that can be applied. So when it comes to trying to create a coordinated assessment to test your system, you're getting a lot of options to choose from that can be a little overwhelming and a little too much to select from. So we try to make the user experience a little bit easier here of getting a system that will understand what it is that you want to test for, and then will select those attack patterns for you and execute them against the targets. So the agent-led system, based on what you want to test, will come up with these testing strategies. It can scale those beyond what humans are capable of. It can come up with new synthetic prompts that are, which extends the curated data sets to generate new types of prompts. Then it can use AI to apply manipulation techniques against these prompts and weave them into different conversations. So all of a sudden, the things that you would need to have a lot of knowledge and expertise to try and come up with these assessments, in a way, is now more outcome oriented. What are you really testing for? What is it that you want to look for? And that's how we wanted to treat this approach. And we'll dive into a little bit of the architecture here. Julie, you can please move on to the next one. So the architecture of our system relies heavily on a pattern that many of you will recognize. We have an orchestrator agent that essentially is your team lead. It is what decides how everything's going to go. And then you have specialized agents that will help execute those tasks. The way the system works is when we have multiple tests that we want to test for, we can create a lot of these attack strategies in parallel. These attack strategies are then handed over to the specialized agents where they will act on them. Every turn, these specialized agents will provide feedback on all the results of that turn back to the orchestrator, where all of that continuous feedback gets fed back into the system for the next iteration. And we'll dive into a little bit more into the orchestrator itself next. Julie, if we can go. All right. So what is the orchestrator actually trying to do? There's several steps happening with the orchestrator agent. The first thing it's going to do is understand, as I mentioned earlier, what it is that you want to test for. We took the approach, and this was, very inspired by the existing frameworks between OWASP, MITRE, and NIST, where they provide clear testing guides and test definitions for different AI application, agent application, LLM vulnerabilities. There are clear objectives. For example, OWASP LLM 01 deals with direct prompt injection. LLM 02 deals with indirect prompt injection. Those test definitions tell us what a prompt injection is, what are the attack vectors of it, what a successful attack looks like, and what a failed attack looks like. So what we did is we took those test definitions, we give them to the orchestrator agent to interpret that test and understand it. In a way, now the test is written in a human language, but then handed to the agent system to interpret into workable parts. And this was, we mentioned a lot of issues with LLMs and AI application being non-deterministic. How do we manage that? We force the LLM to classify the test interpretation into a known structure so that then the rest of the system can interpret that. Once we have that structured test interpretation, the orchestrator agent can then determine what strategies to select for the attack, determines what type of specialized agent should be used. And this is all part of the config. You can, choose what type of attack agents you want. And then once all of that plan is put together, it's handed off to the next part, which is our attack agents. Now, part of the orchestrator too is that after the agents execute that iteration of the attack, it analyzes their results, analyzes how and looks for different patterns for the target, and then maintains all of this information in memory to be reused by the system, and then also to be used again in the next iteration for that attack. The next part here, we have two different types of specialized agents in the system. We have attack agents, and the next part is going to be about the evaluator agents. In this part here, the attack agents know how to exercise the target and evaluate the response from that target. So, how we mentioned earlier, we have, we started our journey in single turn attacks, moved into multi-turn attacks. The same pattern evolved as we were building the AI agent system, where the first specialized agent was our single turn agent. It uses the same concept. We have curated data sets. It samples from them based on the test definition of what it's trying to test for. It has access to all our manipulation techniques as tools. So it makes tool calls to apply these manipulation techniques to the prompts, and then executes this attack against the target and evaluates the response from that target. And we'll get into the evaluation here in a little bit, but essentially the single turn agent will have access to a specialized evaluator agent for that specific test. In the multi-turn agent itself, it needs to take it a step further, because it iterates on the full conversation for that attack iteration within itself. So, where a single turn agent only needs to make a couple calls to the attacker LLM to set the attack and then calls the target, the multi-turn agent is continuously building that attack conversation against that target. It has access to both our scripted multi-turn algorithms and our dynamic multi-turn attacks. And here's where things get really interesting, because we've been able to achieve new novel attack techniques by allowing the dynamic auto red teaming part of it be fully dynamic. We don't control the instructions for how the conversation is going to be generated. The conversation topics are generated by the orchestrator strategy planner based on a dynamic multi-turn attack. And then those are fed to the attacker LLM to generate that conversation. So in a way, we can allow the system to explore new novel approaches for attacking, to come up with new different ways. And it can be different every time, because you can give it a different test interpretation to test for in a dynamic way, give it different knobs to configuration knobs on how many tries to try, how many iterations to try for certain strategies and things like that. And then it can come up with different novel ways. With this system, I have to say, best approaches have been seen when we use very high iteration numbers, where there is continuous learning happening. And this is where it really shines for more of a, you want to do some exploration in red teaming and try to come up with new different ways. Now, if we move on to the evaluator agent, this is where we couldn't use just the same evaluator for everything. If we wanted to have different test interpretations that test for different things, we wanted an evaluator agent that adapted to that test. So the solution to this was, when at the very beginning, when the orchestrator interprets your test definition, comes up with that test interpretation, it then creates an evaluator agent that is based on that test interpretation. So while there are some basic things in the evaluator agent to test for, it's always looking for harmful stuff. It's always looking for things like that. It also is looking for specific specific items that are defined by your test interpretation. So for example, when I mentioned earlier, when we do a test interpretation, we capture what's a successful attack look like, what's a failed attack look like. So the evaluator agent is made aware of all of these different parameters. And so as it's evaluating those responses, it knows that these are the things we want to look for. This now will take us into how do we manage to have all the agents function this way. Two things. First, there's what we call the Atlas config, and this was a unified configuration where we determine where you can configure the number of iterations per strategy, the number of iterations total. You can configure how many manipulation tools you want to sample. You can configure how many prompts. So there's a lot of different knobs that can be turned, but it doesn't really change how the system functions. It just changes how many times we're going to iterate over something, or how many previous runs we're going to pull up to build historical learning about that system. So part of knowing the target is knowing what triggered a refusal from that target and what triggered a successful attack, so that can be interweaved into the new attacks. Now, having a shared config and shared services. So where the shared services, this is where we centralize all the different tools and generators and evaluators. We must maintain context isolation between the tests. And this is done in a way where each test gets its own conversation manager to keep track of what's happening for that test interpretation. And then the global learning about the target is mostly focused on learning about the target itself, independent of which test we're executing. So we try to maintain that context isolation between the different test definitions so that we make sure we're testing for the right thing. But at the same time, we share the learnings about the target itself so that each agent, when it's executing against a target, it has access to those learnings. It helps us keep the same resource pool shared between all of them. And as we're iterating, once we're done, we have a full state of that entire run that we can export back into our platform system so that we can view the results there. As I mentioned before, our frameworks support right now covers OWASP, LLM Top 10, AI application testing guides, Top 10 agentic application. This was the Agentic Security Initiative by OWASP, MITRE test definition, attack test definitions, and NIST definitions as well. Some of them were available as is, and some of them we curated together from these frameworks. Right now, an honest lay of the land, we've achieved just a little bit over 60% of these coverage over all of these frameworks. Some are traditionally out, like just not achievable with traditional red teaming, but we're continuously now working on adding more manipulations, more techniques, more specialized agents to close that gap rapidly. Again, as the stack is advancing, we're trying to advance just as fast with it. I think this is just gives us a quick overall of the agent system so far.
Right. I just want to jump in and say, with these supported frameworks, it gives you structure to your results. So just instead of having like tons of data and your takeaway is, wow, we've had some, weird behavior, you can basically say, hey, our test results have mapped to this known risk category with defined implications. And, here are some of the recommended controls. So it shifts from just raw data and a lot of data to structured insight where the results can be usable, right? So, data everywhere, yeah, it's good, but you actually need to be able to action on that data. So having results mapped to this is super important.
Absolutely.
Too. So,
Absolutely.
yeah. All right. So at the end of the day, the goal here isn't to do testing for testing's sake. It's to reduce real world risk. I'm going to say that again. The goal isn't to just run more testing. It's to reduce your real world risk. Surprisingly hard to say. It's a tongue twister, but that requires that you take a different approach than security has traditionally gone after applications for. And when you move to the agent-led approach that we've just described, you're able to scale testing in a way that matches the complexity of the system, and you're not limited to just what a human can do manually, right? Humans are great; they're an important part of this process, but we need to sleep, we need to eat. Like we just can't scale as fast as the machines can, and with a system like this, you can start uncovering vulnerabilities that only exist across multiple steps, across multiple interactions, across time, and at the same time, you're reducing that manual effort. So again, we want to give you a way to keep pace with evolving AI threats. So turning testing from just a checkbox of, yep, we did it, to something that can actually meaningfully reduce your risk. So you understand how your AI systems actually fail and what you can do about it. So with that, I am going to hand it over to Or and she is going to show us it in action.
Thank you. Yes, I'm going to add some visuals to the color provided by Amer and Julie today. I am in the TrojAI platform, primarily focused today on Detect, right? AI red teaming. There are a couple components, right, that help bring this solution together. The first and very important to make agent-led red teaming function is having targets to test and also targets to use or models to use to fuel the agents that are used for evaluation. And so in the target registry, you'll see I have a slew of different types of targets that I'm testing, different types of applications, different types of models I'm going to be using for both evaluation and testing. Registering a target is relatively straightforward. You give us the name, the location, any sort of authentication we need to make inference to that target, and then save it here for testing. But beyond actually having the target registry or the models or endpoints we're looking to test, there are a couple other components that make agent-led red teaming run. The first is that test definition component that Amer just walked through, where we give the models or the agents running these tests different definitions for what they're looking to achieve. This both benefits the orchestrator, right? So it knows how to put together different schemes for the attacks, as well as the evaluator agent. But we break out these test definitions against different compliance frameworks for today. You can also run these tests against individual definitions. So let's say you just want to run an evaluation against the concept of a jailbreak or indirect prompt injection. That can be done one-off as well. But the definitions is what feeds the agent core and allows agent-led red teaming to function. Beyond that, you do have to set specific models to use both for attacking and evaluating. This is a set it and forget it kind of feature where you select one time what attacker model and evaluator model you would like to see used by the agent-led red teaming system. You'll see that on the attacker side, I opted for an obliterated model, so a model that has been stripped of its security controls or guardrails and is more apt to come up with adversarial examples for me. And then for my evaluator model, I'm going to be using like a mini version of GPT-5.4 that can quickly assess the information and provide context to whether or not my attacks were successful. And so with all these components together, I can actually start running a red team, an agent-led red teaming configuration. I will show you here that you can also run the exact same parameters against multiple models at the same time, multiple targets at the same time. So I will select a handful of different targets and then opt today for the agent-led red teaming approach, right? Where all I do is select the framework, again, pulling those test definitions that we reviewed earlier, confirm and run. And you'll see in the configuration, my evaluator selected, my attacker is selected, so all of that is good to go here. And if we open up back in the target registry, we have some running tests against these targets. And you can also see it under test results. So it has started to run. For the sake of time, I'll show you an example of what the results look like and how the results of the agents come together. You'll see here that I ran an evaluation using, I believe, MITRE ATLAS in this example. And I had some hits against things like jailbreak, data leakage, and prompt crafting results that are interesting. If I were to open this up, you'll see that there were multiple different attempts for these jailbreaking evaluations They're all outlined here, with both the technique and the strategy outlined pretty head on for you to review. But we really do try to call out as overtly as possible when something went awry, when we do have some sort of um, a finding that is more concerning, where the agent-led red teaming system will actually pull from the evaluator and explain exactly what went wrong. So in this case, the conversation or the interaction with the target is here for you to review. You can read through it in detail if you wanted to, but ultimately what happened is we were able to get, or in this case, our HR application model to bypass some standard safety controls by getting clear instructions on how to manipulate certain files. So the evaluator always gives you reasoning, behavioral analysis, and some recommended next steps on how to best mitigate for this risk. Whether it's to continue testing, whether it's to retrain the model, whether it's to implement downstream controls as well, which you can do using something like TrojAI Defend, which will apply runtime protection as these applications are being used. And so making these components very easy to digest. Similar findings can be reviewed for data leakage or for prompt crafting, where we can get the model to come up with inappropriate tokens, right? So behavior that we don't want to see, right, for models that we might be implementing in production. This is agent-led red teaming at a high level. You'll see per individual target as well, right? As I run these evaluations, I have a high-level understanding of how my risks break out across these different frameworks. And so as I continue to evaluate these different targets over time, I can also assess, how they're performing against different core security frameworks over time. And that is it for me, Julie. I can pass it back to you.
Sounds perfect. We're really close to the Q&A, so if you have any questions, this is the time to pop it in the Q&A box. Before we get to that, just a little bit about who we are. So TrojAI is an AI security platform. We have two main components. We have TrojAI Detect, which is what we've talked about today, and red team's AI models. And it does this pre-production and in production. And we also have TrojAI Defend, which is a runtime guardrail that also has an MCP component and a browser extension component, so you can monitor traffic in real time. We are model and cloud agnostic, so we can run anything from frontier models to open source to homegrown models. We work in any private cloud, any public cloud. We're enterprise scale, and if you're interested in learning more, you can learn more about us at Troj.ai. And from there, I'm going to move on into the Q&A. So give me 1 second while I am able to open that on my own screen. The menu bar likes to hide on me. So, okay. All right. So one of the questions that I have is how often do I need to test? If that's a good question for you, or like, is this a one-time deal or?
I would say that it depends on your own understanding of risk, right? And your own risk framework. Typically, when I work with our customers, it's to identify based on their categories of accepted risk, how frequently their program mandates testing, and work from there. So sometimes it's monthly, sometimes it's quarterly. I guess general advice is to not test more frequently than you can, I guess, handle the data that comes out of it or implement some sort of controls and changes. So it really does depend by the use case. Um, but hypothetically, you could run this every day. I think my recommendation is probably monthly or quarterly, depending on the use case.
All right. Okay, next question is AI models, particularly frontier models, are improving um, their security day by day. Do we need a solution like TrojAI? I will take that. Um, this is, something I think a couple of years ago, security from, frontier models, there's definitely a lag, and they've done some pretty decent work in catching up. But the fact of the matter is, at the end of the day, they are um, AI companies. They're worried about the data science behind it. They are not worried about the security of it first and foremost. We are first and foremost concerned about the security, and that is the thing that we focus on solely. And so, much like you wouldn't expect a database to protect itself, you really can't expect a model to protect itself. You do need these external guardrails that are testing and looking for flaws. Also, due to the nature of how these models and agents are built, is that they're not deterministic, and so you need to understand how they work in your specific environment. So there's a lot of variables that go into that. Amer, or do you have anything else to add to that at all? No. Okay. All right. Nice. Okay. Question we have here is, um, if I bring TrojAI into an air gap environment with no internet, does it still work? And actually, this is someplace where we have some really significant advantage. Who wants to take this one?
I can help with that a little bit. So, while yes, some parts of it um, can work, all the scripted algorithms, all the curated data sets, all the single turn and multi turn, like the basic operations without external access will work. But if you go into agent led red teaming, you want to have access to an LLM. So in an air gapped environment, if you have the infrastructure to host your own model locally within that air gapped environment, then you can take advantage of that
Yeah.
agent red teaming. Excuse me. But
Yeah.
if right, go ahead.
Oh, no, no, go. Finish your thought.
So really, it's just if you have the infrastructure in an air gapped environment to host your own LLMs, then 100% this is a usable system there. That's the only requirement is you need access to an LLM to generate those attacks.
Yeah. Yeah, I just want to add to that, like typically in our largest enterprise customers, we are deployed on-prem in either like a private cloud or a private data center. And that is so, you're not exposed to sort of the greater internet. And that is really one of the big advantages of how our system is architected and how it's deployed. Um, so yeah, definitely we understand that these systems are touching your most sensitive data, your most sensitive applications, and you want that air gap. You want to protect all of this infrastructure. So it's something that we do very typically in our largest deployments. Okay. Um,
There's a question, Julie, I want to address quickly, I think.
sure.
I know it's by an anonymous, but still, it's a worthy answering question. How do we prevent the red teaming agent from collaborating with the AI it's assessing? Um, this is a really good question, and I think I want to address it by explaining a little bit of how our agent system is built and how it differs from the popular concept of what an agent is. So when we think of agents nowadays, we immediately think of the likes of coding agents or OpenClaw, for example, where they have autonomous style operations capable of doing things unstructured. The way we built our system is a little different than that. We built it so that it has structured inputs and outputs, so that there's a little bit more predictability in how it behaves. It is not a React style agent. It is not a reason and act freely and do whatever you want type agent. There is a lot of controls. And the way we manage that is by handing the state and tasks between the agents in small contexts, so that when we are handing a task to the single turn agent, the context in which it understands its task is very simple. Here's the strategy. We want you to come up with a prompt that does this, and then execute it against that target and give us the response. That's it. So that separation of concern between the attacker agent and the orchestrator and the evaluator agent means that each agent has a very specific task. All of them would have to be able to collaborate for this to happen, and we just don't have that mechanism available to them. It's just not something that they are capable of, because we put these hard lines in between them and what context is given to each agent and what task is being asked of it. So that separation and isolation is how we prevent those systems from collaborating with the targets.
Great. Thank you so much. I think that's a really good question to end on, and we are at time. So again, I just want to thank everybody for their time today and for their great questions. If you want to learn more, please check us out at www.TrojAI, and we look forward to seeing you all next month. Thanks so much.